Well, I'll say good morning to everyone. So this is class number 16, and I gave class number 15 yesterday, so I would guess that many of you have not watched that yet, but hopefully you will before the semester is over. So how many classes are there during the semester? There are 30. And so this is 16, so I guess we're beginning the second half of the semester today. So there's homework here, which I hope you pick up so I don't have to carry it back upstairs again. And so I guess there won't be a lecture here Thursday, so that's when, if you haven't listened to the lecture I gave yesterday, you can listen to that on Thursday on your computer. And then next Tuesday, what happens next Tuesday? Oh, exam, that's right. Okay, good. I'd forgotten that. I knew something happened. I knew I was going to be out of town, which I thought it's best to be out of town when you give an exam. And so I'll be in the great city of Rochester, New York, where the weather doesn't look quite as good as it will be here. Okay, so we've talked, well, we're talking about the measurement of surface structure. We've talked before about a white light vertical scanning coherence probe type interferometer. And I'll talk again today about an interference microscope, but this time we're going to do phase shifting with it. And some of what we learned before will also apply here. So this is going to be non-contact. So compared to the stylus, for example, thought of this. I think I told you I thought this would put the stylus out of business, but it didn't do it. But certainly thousands of these are used throughout the world. So it's going to be a non-contact measurement. You can get two-dimensional measurement or three-dimensional measurement. It's basically a microscope system, and maybe there's even eyepieces on it, so you can look in and see the surface, or not eyepieces, at least you'll have a CCD array and camera, so you can look at the surface. It will measure down into the sub-angstrom range on height, not on lateral dimensions. Lateral dimensions are, well, smallest you're going to get is something on the order of the wavelength of light. But the height is going to be in the angstrom or smaller. And it's going to be very fast. And it's going to use phase shifting. It's going to get data into the computer fast, and then there's all types of analyses that we can do. So we're going to use source, although in this case we're going to filter it. People have tried to make these microscopes using lasers, but they don't generally work too well. And the problem is, in a microscope, well, you have a microscope objective which has many elements in it. So you have many surfaces, and you have many chances for reflections that you don't want, and so you get a lot of fringes you don't want. And so the white light or short coherence length source, you still get these reflections, but you won't get these spurious fringes that I talk about all the time and that I hate. It will work with multiple wavelengths. We've talked about multiple wavelengths before for measurement of large steps. The focus is going to be easy to determine. The system is just what we saw a couple, 3 classes ago, except now we're going to put in a red filter, or put in a filter. It doesn't have to transmit red light, but often they do. Most common wavelength, I guess. The source here, well, it might be a tungsten halogen bulb, or more likely now is LEDs. And then we're going to have some type of interference objective down here. And we've talked a little bit about the Merrow, but after last time I talked about Merrow after class, there were a few people came up to me with questions on the Merrow, so I'll talk about the Merrow again. And then we're also going to talk about using a Michelson and using a Linic down here. The translator now is just going to do moving the reference surface, and so we're just doing phase shifting. So this is probably a PZT that's going to cause a translation here. And there may be some objective up here. Sometimes I make it so you can change the magnification up here if you want. And then our detector interface to a computer. And so the computer will read out the detector and also control the voltage to the PZT to control the phase shift. And as I've said before, I'm not just illuminating a point here, but I'm illuminating some area. And so I'm going to image an area up here. So I'm measuring a whole area at a time. And the Merrow, which we've seen this slide before, but there were still questions on it, so let me come back to it. And I have to say I really like the Merrow. And it was almost an accident that I even learned about the Merrow. Years ago, I used to have my office on the 5th floor. And across from my office was a lab that had a lot of microscopes in it. And it belonged to a professor who retired from here a number of years ago now, Bernie Serafin. Anyway, the lab door was often open, and I would wander in there and play with the microscopes. And one system I played with was the FICO, which I talked about yesterday in the last class. Fringes of equal chromatic order. But another one that I played with was the Merrow, and I had never heard of the Merrow interferometer. And in fact, I think it was pretty, wasn't known about by a lot of people. And in fact, the first time I published a paper where I talked about the Merrow, I got a letter from the professor who had taught me interferometry when I was a graduate student. And the letter said, "What in the hell is a Merrow interferometer?" So I guess he had never heard of it either. But now it's the last few years it's become pretty commonly used. And as we said before, I mean, it's very nice that the paths are matched here. We have the same amount of glass in both the reference and test beams. There is a central obscuration, and I think that's what the question was after the last time I talked about this in class. So this central obscuration is going to be the size of the portion of the sample you're looking at. So this might be a millimeter, it might be a couple millimeters, depending on the particular objective. And the most common objectives here are 10x, 20x, 50x, and occasionally a 40x. So, you know, this will change the resolution properties of the objective a little bit. We'll emphasize the higher frequencies a little bit because of the central obscuration. And it's going to limit how large a field of view you're going to have here. Because if I try to use too large a field of view, that means that the reference is going to have to be larger. And that means that I'm going to have more central obscuration. And so that's really why this is used at sort of the medium magnifications, is that if I try to get to too low a magnification, large field of view, then the central obscuration will become too large. If I try to get to too high a magnification, well, the problem there is I have all this glass in between the objective and the sample, and I'm using up part of the working distance. And so it's hard to make this particular objective work at a much higher magnification than 50x. So this typically has, I don't know, maybe a 30 to 60% reflectivity. And the best one of these has, the reference has maybe a 3 angstrom RMS roughness. It's pretty hard to get one that's better than that unless you build your own. The commercial ones are on the order, the good ones are on the order of about 3 angstroms RMS. Any questions on this? Because this has become, well, I think really since Wyco introduced this in our products and then other people began using it, it became probably the most popular interference objective used nowadays.
So that in this you having to use a extended source?
This will use an extended source, yeah. It works very fine with an extended source here. And paths and everything are matched. That helps you in working with an extended source, not just temporal coherence, but also spatial coherence. And yes, any other questions on it? So that's the Merrow. And as I said, it's used generally at medium magnifications. At low magnifications, people often use a Michelson. And so here we have the objective, here we have a cube beam splitter, a reference, and a sample here. And so with a cube beam splitter, again, we can match the paths in the interferometer, and we have the same amount of glass in both arms of the interferometer. So you don't have to worry about a real narrow bandwidth. I said I put a filter in here. It might have a band pass of, well, it could be as narrow as 10 nanometers, but typical numbers are more like 40 to 80 nanometers. It's not a real narrow bandwidth here. Anyway, so same amount of glass, paths are matched, no central obscuration, so we can use we can have a larger field of view. That's why we have lower magnification here. And but you have all this glass in here, and so the actual working distance, the distance from the last element here to the sample, is generally pretty short. And a problem, I think I mentioned this before, but I can't mention it enough times, I guess, is that you have to be very careful here that you don't crash the objective into the sample. Everyone does it, I have to say. Even I've done it a few times. But you have to be very careful. And typically what I would do is in trying to focus this, I would move the objective too close to the sample, but I could look, and see as I bring it down. And then to find focus, I'd be moving the objective away from the sample. Because if you go the opposite way, you may miss focus, and the next thing you know, you're going to crash into the sample. So it's best to initially set it too close, where you can look at it, making sure you're not touching it, and then you move it away to do focus. And nowadays, I mean, with a computer connected up to this, you can have an autofocus that looks for fringes, and and so you can find the focus automatically. The other thing that sometimes you do, you put a hard stop in here, and so this cannot move down too far to hit the sample. So that's the Michelson. It's low magnification. Maybe the lowest you see is 1x. A real popular magnification for this is 2.5x. So 1, 1.5, 2.5, 5x. Michelson. Now we go to the Linic. And this is the, I don't know if I call this the Mercedes or if I call this the Lexus of microscope objectives, which means it's rather expensive. So what we have here is a beam splitter, and then we have two objectives. So these are matched objectives, same amount of glass in the two objectives. I mean, not only do they say the same thing on the, have the same part number when you buy it, but you really have to, just because it has the same part number doesn't mean it's exactly identical. So you try to, when we used to make these Linic interferometers at Wyco, we would buy maybe 10 objectives and then swap them back and forth to match them the best we could, and we'd always end up with 2 or 3 out of the 10 that we just couldn't match. So we'd send them back to the supplier, And the supplier, of course, would always try to send them back to us without our knowing it. But we'd write down the serial number so we'd know if they're pulling something on us. So anyway, you have a beam splitter here, you have your objective, you have a reference mirror. Another identical objective in a sample here. So again, the idea is the paths are matched. We have the same amount of glass in both arms. And we have nothing between the objective and the sample. We don't have a beam splitter here. The beam splitter is before the objectives. And so we can make higher magnification systems here. 100x, 200x, NA 0.9, NA 0.95, high numerical apertures. We still have pretty short working distances, for sure, fractions of millimeters probably. But we're getting all the working distance we can from the objective. We're not wasting working distance by putting in beam splitters or pieces of glass or stuff. So I show this for high magnification. I mean, you could make these for 20x, a 10x, a 1x, or whatever. You could. The Linic would work for any of these magnifications, but you generally use it only for the higher magnifications because this thing costs too much money, and you already know I'm cheap, so you don't want to spend any money you don't have to. And so you only use these when you have to, which would be the high magnifications. Sometimes you might go down to a 40 or 50x here. I mean, you could do a pretty good job here with a 40 or 50x, but you don't have as much working distance. And there are cases when you just need all the working distance you can get, and so you would put a lower magnification. Also, if you wanted to make a polarization type interference objective, so that the test and reference beams have orthogonal polarizations, it's a lot easier to do that using the Linic than it is, say, using the Merrow here. And so at 4D technology, we do make low magnification Linics because we want the test and reference to have orthogonal polarization. So a summary here is the Merrow, medium magnification. We have a central obscuration, so that limits the field of view. And we have limited numerical aperture because we have that glass between the objective and the sample. A Michelson you generally use for low magnification. You have a large field of view. The beam splitter limits the working distance. And there's no central obscuration, so you can have the large field of view. And then the Linic, you generally use it large numerical aperture, large magnification. The beam splitter comes before the lenses, so it doesn't limit the working distance. And generally they cost a lot of money because you have to have two objectives instead of one, and they generally have to be selected objectives so they match one another. I might also say with the Linic here, I mean, there are other problems in making these with large numerical apertures that you have a short depth of focus. Any small motion here, change in the distance between the objective and the reference mirror bothers you, so you have thermal expansion problems, and just aligning these. It's a much more complicated interferometer to build, and I don't know of any of the microscope manufacturers, to the best of my knowledge, the Nikon or the Olympus or the Zeiss. I don't know of any of them who make Linics anymore. They used to, but the people who sell these phase shifting interferometers end up making their own Linics. Any questions on this? Okay. So I'll just show a picture of one of these. This is one off the Bruker website. So it's one of the current ones. So here we have the objectives probably mounted on a turret there, so you can change the magnification. And source, which I think is LED in this case, and camera and everything are up here. And I think this system probably works both with the phase shifting and with the coherence probe, vertical scanning approach. I may have shown you this picture before. I like it so much I show it every chance I get. Years ago I used to have it on my office door. I liked it so much. But just white light interference fringes. Little wiggles in here. This was looking at a diamond turn surface, so we're seeing a lot of grooves in the surface that gives that structure. So in this case, well, I'll say in general, you know, that the center fringe, where the paths are matched, it may be a bright fringe or it may be a dark fringe, depending on your configuration and the phase change on reflection. It may be, or could be a polarization type interferometer, or it could be something in between. If you have a metallic, beam splitter, metallic coating, phase shift can be anything. So you never quite know if whether the paths are matched. If, well, once you build the instrument, you know, but beforehand, any given instrument, the paths are matched at a point where the fringes may be light or dark or something in between. So as I said, this is for a diamond turn surface, and this just looks at a scan of what the surface looked like. And so this had an RMS of 11.8 nanometers and a peak to valley of 48, and an RA, average height here, of 10.1. And this is looking over, this was a 20x objective, and for this particular system, the 20x objective gave a field of 660 microns. So a Merrow, most likely a Merrow was used in this measurement here, and the field here is 660 microns. So the reference surface in the Merrow had to be just a little bit larger than that. And then just looking at a 3D plot of, I don't know that's the same surface, but another diamond turn surface. And this is looking over about 99 microns, so this was a somewhat higher magnification. And then I went to the Bruker website and just got some what I thought were pretty pictures. And they never put any numbers on their pictures for some reason, but this is some type of grading, I guess. That's kind of cute. And this is a diamond film. Height scale is. The last one here is a picture we took out at 4D. This is using a little profiler, phase shifting, you see the objective here. And it's using the polarization technique where we have the wire grid polarizer array, so we're getting all 4 phase shifted frames at once. And this is just to show that, you know, you could mount this on a robot here, and you get a fair amount of vibration, but we still could make pretty good measurements. I was kind of impressed how well that worked. So that's taken well, a few years ago now, or maybe the summer. I guess it was during the summer. So any questions on measurement of surface structure, surface roughness, surface microstructure? So that's the chapter 6. Now remember that the exam will just go through chapter 5. And if I looked at my schedule, this should be the end of the class right now when I finish. But I'm slightly ahead of schedule, and we have time left. So we will go on to chapter 7. So we've talked a little bit about the testing of flat surfaces and mirrors, but we're going to talk a lot more now about the testing of different flat surface optical components. And we're going to start off here, and we'll say just a little bit about Fizeau and Flaming Green. You're all experts on the Fizeau and Flaming Green anyway, but I have to say a few words about it. And then we'll go on to the Ritchie common test, which we've not talked about. And then we're going to talk about what I call a naked eye test, which is kind of cool. And then we're going to talk about testing of windows, using interferometers and using autocollimators. And then we're going to talk about testing of prisms, using interferometers, a goniometer, an autocollimator, and another naked eye test. And then we're going to talk about corner cubes. I love corner cubes. And then testing of diffraction gratings. And the last topic is index, measuring index variations. And I'm not sure that belonged in this chapter, but I had to put it someplace. And so this seemed like as good as anything else. So mirrors. So if we're going to measure the flatness of a mirror, so we've been talking about the roughness, now we're going to talk about the overall flatness. You know, we're probably going to use an interferometer nowadays. And the best interferometer depends on, you know, what you have available and the size of the sample and so on. And probably the most common interferometer for measurement of surface roughness is the Fizeau, which you're all experts on, so but I think I need to show one slide here. And so here, I mean, nowadays we generally use a laser, but you know, not always. If we don't use a laser, then we're probably going to put the two surfaces pretty close together. And we'll either look down here with an eye or CCD camera or something and look at the interference fringes. And I just took some interferograms. I think I copied this out of a book that Eric Goodwin and I put together. Just saying, you know, if we have some air wedge here, so have tilt between the two. If we have a flat, well, we're going to get straight, equally spaced fringes, as we know. If we have a cylinder, so it's going to vary in the x direction and be constant in the y direction, we'll get, you know, straight fringes, but they're not equally spaced. And there's going to be some region here where the fringes are most widely spaced, and we can move that portion back and forth by changing the tilt. And if we have no tilt like I have down here, then that would be in the center, but by introducing tilt we move it around a little bit. And then if we have cylinder going the opposite way, so now it's going to be linear in the x and the cylinder is along y. Now the fringes are going to be equally spaced here, but they're not going to be straight. Okay, so they'll be curved. And if we have a sphere, well, the fringes are going to be curved, but now they're not going to be equally spaced. So they look a little bit alike, but here the spacing is going to vary because of the sphere. Here the spacing will be constant here. If we have no wedge between the sample, well, if it's flat, I mean, it becomes a single fringe. And if you're trying to measure errors by looking at how straight the fringes are, of course this isn't going to work, but if you're using phase shifting, out the fringes. Because remember in phase shifting we always get this double frequency error. If the calibration is off just a little bit, we always get an error that is double the frequency of the fringes. Well, if I have one, then I don't have the problem with that. And so phase shifting, you generally fluff out the fringes the best you can. And then just showing the cylinder, as I said, you know, here we had cylinder with tilt. Here we have cylinder without tilt. Sphere, whether it's convex or concave, is, you know, the fringes are going to look the same. Oh, how in the world could I tell if it's which one is convex and which one is concave? How, if you had an exam question on that, what would your answer be? What? Yeah, push on it a little bit. So the fringes move, and see if they move in or out. I'll let you think about that between now and next Tuesday. Not that I'm asking a question on that on the exam, but you might think about it, okay? And this is a saddle, so this is sort of, you know, astigmatism, but curved convex in one way and concave in the other. And I guess these little points here were indicating where it's touching the reference surface. So anyway, there are millions of interferograms, and we had some and other ones in the notes. And if you go to my mathematical, I generate all kinds of crazy things, and always fun to play with. So this, you know, this is a very common Fizeau, you know, 1862 has been around so long. It's had 150 years. Amazing, still used. They said, you know, as we said before in class, you know, if you're testing flat surfaces, you just need one reference, so that's good. Putting these two surfaces together, pretty easy to scratch one or the other. And so nowadays, it's probably more common to use a laser source. Same idea for the Fizeau. We talked about this before. Just that it's no longer, I mean, we don't have a coherence problem. And so the two surfaces don't have to be put real close together. But now, I mean, we have long coherence. I keep, you know, always mentioning these spurious interference fringes, which have driven me crazy over the years. And you go to a laser, spurious interference fringes. So that's a nice thing here. You don't have that problem. Here you do. But this is probably the most common way nowadays to get around the scratching of the problem. How do I get rid of the reflection from this first surface? Would I put an expensive anti-reflection coating on it? You could, but I wouldn't do it because I'm cheap. Wedge. Put a wedge between the two surfaces. And then I don't show it, but there's always a small aperture down here. So the reflection off of the surface you don't want will not get down here. So I would use a wedge. I probably typically use a wedge and a low, inexpensive anti-reflection coating, just so you can tell, you know, you're getting two reflections, and you want to tell which one came from the first surface, which one came from the second surface. And so here, the only high-quality surface we really need is this last surface, the reference surface. These other surfaces don't have to be high quality. The error becomes worse, so if I have errors back here, as I change the separation between these two surfaces, so the light is traveling different distances, and if it's, you know, if it's not at normal incidence here, you get this old 2D cosine theta OPD change for light going through here at different angles. And so if I have aberrations in the beam going in here, and I put this mirror a long ways away, the 2D cosine theta, you know, theta being the error in the direction of the beam, and theta will, if I have aberrations, theta will vary across the beam, and so 2D cosine theta, d being the distance between the two, will vary, and I'll get an error. So if I'm going to put this far, far away, which I normally don't, but sometimes you have to for some ridiculous reason, you can get an error from the beams back here not being perfect. Okay, comments on a Fizeau. Okay, let's say I'm going back here to this Fizeau, look at it this way. It could have been the other one, but this is easy to think of. If I put two surfaces together and I get straight fringes, do I know I have flats? The answer is no. I mean, one could be concave and the other one's convex. If I'm putting two surfaces together and I get straight fringes, all I know is that the two surfaces match. I don't know what the shape of either one is. And so the way to really tell if the two surfaces are indeed flat is to have three. So I will compare A with B, A with C, and B with C. The only way I can get straight equally spaced fringes in all these situations will be if the surfaces are indeed flat. So to make sure they're really flat, you need to use three surfaces, not two. And at the end of the semester, we're going to, close to the end of the semester, we're going to be talking about what I'm going to call absolute measurements. And we'll find that if we have three surfaces, I can actually do an absolute measurement and determine the shape of all three surfaces, regardless what they are. So, we also talked about Twyman Green earlier, and just mentioned again, that's a very good way of testing flat mirrors. And probably the disadvantage here is that I have to have more high quality optics. So what high quality optics do I need in this interferometer? I forget what surfaces, which components have to be good? Someone must.
Reference mirror.
Reference mirror, okay, reference mirror has to be good. Anything else?
Beam splitter.
Beam splitter has to be good, yeah. Hate beam splitters, give me so much trouble. Beam splitter has to be good. I guess one good thing here, you could match the intensities of the, well, I in the other one too, but generally for testing, well, for testing anything, you have the ability to easily replace the reference mirror with different reflectivities, and so you probably have a little turret there with 2 or 3 reference mirrors in place here. Okay. What was another name that we used for the Twyman Green before, when we used a laser? Loop. Remember? Laser unequal, well in this case the paths are equal, but they don't have to be. Laser unequal path interferometer, loopy, L-U-P-I. I remember one student told me this was a leapy, because it's laser equal path interferometers. But anyway, I've never seen leapy in the laser, but I've seen loopy many times. So the Twyman Green and the Fizeau give the same interferograms for testing surface flatness. The Twyman Green is more versatile. I really like the Twyman Green, I have to say. Just a very versatile interferometer. I can make it very light efficient. But it does require more high quality optical components, in particular that beam splitter had to be high quality here. So it's a little disadvantage. But both Twyman Green and Fizeau, both of them are very good for testing of flat surfaces. Okay, so let's say I have either a Twyman Green or I have a Fizeau, and my boss comes along and he says he wants me to test a 1 meter diameter flat mirror. So if I were to do that with this setup here, boy, I'd have to have a big beam splitter here. and big reference mirror. And if I go back here, I mean, a big, well, we often call this transmission flat. And even going back here, if I want to test a 1 meter diameter flat, I have to have a large reference flat. And that can be a real problem. So that's where the Ritchie common test comes along. So this is a test that's been around for who knows how long, a long time. The idea here is that I have a large mirror, and instead of having to have a large flat, what I'm going to do is to have a large sphere, spherical mirror. And it just, I mean, it's more common to have a large sphere in the shop than a large flat. And the sphere can be used in more applications than the flat, I guess. So anyway, the idea here, we'll put a point source there, and we'll reflect the light off of here up to well, off my flat. It's supposed to be a flat, up to a sphere, and then back here again into here. And if I were to do this nowadays, I mean, I would put here either a small Twyman green or a small Fizeau type interferometer like we would normally use for testing a spherical surface. We talked about that earlier. But back in the days when Ritchie Common, when this first test became, when they first came up with the idea, what they would do is they would put a point source there, and then they would look at the image of that point source. And the real thing they were probably after was, you know, I have this flat. Is it really flat, or does it have a small curvature to it? Hard to tell. But by illuminating this flat at a large angle, and I show 45 degrees here, but typically you might even go to 60 degrees. By illuminating this at a large angle of incidence and the light coming back, say this is curved just a little bit. The beam coming back is going to have some astigmatism in it. And I used to derive in class how much astigmatism it had, but I've kind of stopped doing that. If you go to Malakera's book, you can find out more about that. But in any case, this is and I'll give you some numbers in a second. This is a very sensitive test to determining whether this is a flat or if it's slightly curved. And just some numbers, which I got from Malakera's book. Let's say I have a flat that is 1.5 meters in diameter. And let's say I do it at a 60-degree angle of incidence. That turns out to be pretty high sensitivity. So I'm going to make this angle of incidence here be 60 degrees. And let's say there's 5 meters between the source and the flat. So 5 meters here. That's maybe not so critical, but 5 meters here. If this flat has a radius of curvature of 300 kilometers, which seems to me like a long ways, okay? A really long, 300 kilometers, you are going to get a distance between the two foci for astigmatism, the S and T, of 250 microns. Isn't that amazing? I even had to go through those numbers a couple of times to see if I didn't make a mistake. So a radius of curvature of 300 kilometers, and the secret is we're illuminating a large angle of incidence, 60 degrees, gives a distance between the S and T, sagittal and tangential foci, of 1/4 of a millimeter. And so, I mean, we can easily measure that here, putting a point source here and looking at coming back, seeing if it's a point source or a line source, and moving this back and forth and measuring the distance between the sagittal and tangential foci. So this is a very, very sensitive test for determining whether your flat is really flat or if it has a little curvature. Yes?
So right now we're assuming that the flat that we're testing is rotationally symmetric, or if
Yeah.
it's astigmatic, what happens?
Well, I can get to that in a second. That's coming on the next slide. But right now, I mean, that's a potential problem that can throw you off. But we certainly, if we get a distance between the S and the T, the thing we know is that the flat's not. And you're right, it may have some astigmatism built into it, or it may just be curved. I don't know. Well, I'll ask you before I go on to the next slide. How might I tell whether it has astigmatism or just curvature? I'll drink a little bit.
Rotate the
Ah, very good. Yeah, rotate the flat and repeat the measurement.
and the flow have to be very non-astigmatic. That's one of the
Yeah, I mean, I'm assuming here that this is a good sphere. Now we've talked, and we'll talk a lot more about testing of spheres. We're going to talk about 1,000,001 different ways of testing of spheres coming up in another chapter. But we talked earlier in the semester, when we were just getting into the optical testing, we talked about how we might measure the sphere. And so you would measure the sphere. You have to have a good sphere. So if you're putting together your optic shop, you start off by getting a good sphere or making a good sphere. And then you use that in the test here. And of course, it's very easy to get astigmatism here by just mounting it wrong, or just a sag of it. If you don't have a good mount, it's very easy to get astigmatism. But this it's just such a sensitive test. I think these numbers are just amazing here. That that long of a radius of curvature gives you that much between S and T foci. Now it's a large flat, but the real thing that's doing it for us is a large angle of incidence, 60 degrees. Just becomes very, very sensitive. If you go back and look at the basic equations, you'll see that that's true. Now, if I do one more calculation here, and I say, well, how much sag if I have a 300 kilometer radius of curvature, but I have a 1.5 meter diameter flat, the sag is actually about 1.7 waves. So it's more than you think. So once you see what the sag is, maybe this is not quite so surprising. But without seeing what the sag is, I think that's just amazing. And so this was it's still a very common test because people generally don't have large flats. They're more likely to have a large sphere. And so the Ritchie-Common test is commonly used. But nowadays, you don't really measure typically you don't measure the distance between S and T foci. You put an interferometer here and measure the wavefront coming back. Now, if I look at the Ritchie-Common, the advantages, you don't need this large flat. And it's very sensitive to small curvature. Extremely sensitive to small curvature. The problem is, if I'm trying to really measure how good a flat is, when I'm illuminating something at an angle of theta, remember the sensitivity goes down as a cosine of theta. If I look down here, that's a pretty rough surface. When I look at this at a large angle of incidence, that's a pretty smooth surface. It goes down as a cosine of the angle of incidence. And so it's difficult to measure small irregularities because the OPD is reduced by the cosine. Well, it's more difficult. And then this is kind of a little bit related to your question. I may get a null test here. I may do this, and I'm not going to see any S and T foci. I say, oh boy, I have a good flat. But maybe I don't. It could be a hyperbola, just such that the foci here are wherever this point source is and wherever that center of curvature, that mirror is. And so to determine whether it's a flat or a hyperbola, you rotate the mirror 90 degrees and repeat the test. And that's also to check if you have any type of astigmatism, rotating the mirror and checking for it. Checking is see what happens. Do the measurements change? Yes?
So we were kind of talking about the old method where we'd be looking at just the space between S and T foci.
Yeah.
You said nowadays you put an interferometer.
I'd probably just put an interferometer there and measure the OPD.
Okay, so then you can get a surface map.
Then you get a surface, and you have to remember that the sensitivity goes down as a cosine of the angle, and so you would take that into the account. And in fact, if you want to really be good about it, the angle of incidence varies over the sample here. Cosine theta varies, and so you might want to put that into your software too to correct for the variation in the angle of incidence. I mean, I'd use an interferometer for everything. That's my approach to life. But yes.
When looking at the interferograms, would it be getting slightly off with that much amount of tilt in that surface?
With the what? With the
interferograms,
yeah.
It'd be a lot more difficult to measure just because of the amount of tilt in that surface since you're going at such a angle.
Because the amount of
I mean, the wavefront itself. I mean, just trying to interpret the.
well, just because of the cosine theta. Yeah, right. But you have a computer connected to it, and it takes care of the cosine of theta. But if you just look at the interferogram, yeah, I mean, if you don't take into account the cosine of the theta, you're getting an incorrect number. But the software will take care of that. Most of the interferometers you buy in the market today have a setup for the Ritchie common test because it's so common, and it takes into account this cosine factor. Okay, any questions on that? Sounds like our industrial affiliates have come downstairs here for have their picture taken, I think. So did you get some classes canceled today because of industrial affiliates? Oh, building. Oh, good, good. They didn't cancel. I'm glad. That's good. I thought I was clever to be in the other room early in the morning. Okay, so that's the Ritchie common important test. This is not so important, but it's kind of interesting. It's what I call the, and it's going back to the same idea. If I have a mirror here, and this has a little curvature in it, if I look at, if I look at something by looking at the light reflected off the mirror here, and I look at a large angle of incidence, I will see astigmatism. So if I'm looking here at, say, this target over here, so I have dashed lines, horizontal and vertical. If I have a little curvature here, my eye is going to see the astigmatism, and in either the horizontal or vertical direction, these dashes here are going to merge into a gray line. And this is actually pretty easy to see. I've done it many, many times, just taking a mirror and giving it a target. You really, it's very, very sensitive to a little bit of that they say is that, I mean, how much curvature I can detect really depends upon how much mirror surface I use. But it says that the naked eye can detect a radius of curvature up to 10,000 times the length of this surface. So if this surface is 10 centimeters, I could measure up to a curvature of 100,000 centimeters. Whew. That's a kilometer. Just by looking at whether this becomes smeared or not. And it really does work pretty well. So that brings me to this book down here. I mean, this book is old. When I was your age, this book was old. So now it's really old. And it's had a couple of three different names over the years. And this book was first pointed out to me by Roland Shack, and the copy he had was really, really old. And he had given something like $1 for the book, so I had to order it, and I bought it, and I had to pay $3 or $4, and I don't know what you'd have to pay nowadays if you can even buy it. But it has a lot of little things in it like this, which I don't know. I just kind of find it interesting. I would always use an interferometer to measure this, but it's kind of interesting to note that you really can detect such a small amount of curvature just by looking at the astigmatism you get when you go to a real large angle of incidence. Okay, so that's the naked eye test. So let's talk a little bit about windows. So, what's the most common way of testing a window? Well, it's probably an interferometer nowadays. And if I'm going to look at how parallel the two surfaces of a window are, I might use an interferometer. I probably would use an interferometer. But an autocollimator is also very commonly used. So we want to go through here and talk about a little bit about the testing of windows here. And I could test a window with a Twyman green, with a Fizeau type interferometer. But I'm going to have a set of drawings here for testing windows and prisms and different things, corner cubes and so on. And for all of them, I'm going to use a Fizeau. And I'm going to leave out most of the picture of the Fizeau because you all know what a Fizeau is. But I'll just show, well, here's my reference surface, transmission flat. And I'm going to look at the light reflected from here. And then I'm going to send the light through my window, reflect off a return flat, back through the window again and back. And I won't show all the light source and the detector and beam splitter and stuff back here. But everyone understands what I'm doing here. So if I think here for a second, well, first off, I'm going to be going through this window twice. So whatever I'm measuring is probably going to have a 2 in it. So I want to measure the optical path difference going through the window. And right now, I will assume the index of the window is constant. Later, we're going to worry about what happens if index varies. But right now, the index is a constant, and we'll call that n. And so as I go through this window here, well, outside the window, the index is 1. So if the thickness changes by a little bit, delta t, what I'm going to measure then will be n times delta t minus delta t. So n minus 1 delta t. So what I'm measuring here by going through this window twice is 2 n minus 1 times any thickness variations delta t. Okay? And so I'll get an interferogram that will show me that, if I were looking at a surface, at a mirror, I would be measuring twice the height variation of the mirror. In this case, I'm measuring twice the n minus 1 delta t. And most interferometers you buy nowadays connected to a computer will have built into the software, say, oh, I'm testing a window. And you say, well, the index is 1.5 something or another, whatever. And it will automatically do this calculation for you. Okay. Well, I keep talking to you about, lasers and spurious interference fringes because they just drive me crazy. And that becomes a real problem if I'm measuring a window having a small amount of wedge in it. Because I'm going to get some reflections also from both sides of the window. And I can get some fringes I don't want. And if I use a long coherence length source, a laser, these spurious fringes drive me crazy. How do I get around that? I go to coherence link source, and I'm also getting around the effects of spurious interference fringes from other reflections in the test setup. So what I'm saying, if I were to test a window, a thin glass window, put a wedge in it or something, I'm going to get a pattern that's kind of messed up here. I mean, these fringes, they look kind of weird. Right? If I can some way use a short coherence link source, I can get rid of these spurious fringes. So how can I do this? How can I go to a short coherence link source? And I want to use a Fizeau type interferometer here and do this some way. So let's see what I can do. Well, I'm going to describe a technique here that's going to get around the effects of these spurious interference fringes. And it's going to work with phase shift. And I'm going to use this polarization, a wire grid polarizer array. And let's see how this works. So I start off here with a short coherence link source. And typically what you might do is to have a laser diode, which might have a long coherence link, but you modulate it. That will then become a fairly short coherence link source. And so it might have a coherence length of 100 or so. So the beam coming out of here, if I just used, the beam coming out of here, if I just tried to use a Fizeau here with a long path difference greater than the coherence fringes, and eventually I'll go to the next slide and I'll come back. So what I'm really going to do is to have my Fizeau and put my window in here. But I want to get rid of these stray reflections. So what I'm going to do here is take this source. I'm going to send it through what looks a little bit like another interferometer here, where I have a path difference between the two arms here, or a delay. Maybe I want to say a path delay. So coming out here, I'll have two beams with a path delay. And I'm going to use a quarter wave plate, a polarization beam splitter with a couple of quarter wave plates, such that these two beams coming out of here, not only is there a path delay between the two, but the two beams have orthogonal polarization. Okay? And because of this path delay, even if I were to put a polarizer in here, I would not see any interference fringes because the path delay is large. Anyway, I come over here to where I have my Fizeau cavity. I'll get a reflection from here. I'll get a reflection from there. Both these beams will be reflected from both of these. And if I think here for a second, let's kind of read this down here. The interference pattern from the long path source beam, so that's this one here, reflected off the reference, and the short path length source beam reflected off the test. You know, if I'm clever here and I make this distance here equal to the path difference back here, then these two beams, you know, this beam reflected off here and this beam reflected off here, will have the paths matched and they will be coherent with respect to each other. Now the two beams have orthogonal polarizations, but I can put my little polarizing mask in front of my detector here and get the interference pattern that I want. Now I'm going to have other beams present. You know, both of these beams are reflected off of here, and both these beams are reflected off of there. but they won't be coherent. It's only the long path reflected off of, oops, the long path reflected off of here and the short path reflected off of there that will be coherent. So even if I get other reflections in the system, I won't get spurious interference fringes. Well, sometimes it's a little hard to understand the first time you see it, but any questions we're doing? Yes.
So not only does your reference surface have to be good, those two mirrors back there.
Oh, yeah, I mean, I have all kinds of things that have to be good here. This is an expensive system. This beam splitter has to be good. These mirrors have to be good. These quarter wave plates have to be good. Yeah. Money. But I get rid of spurious interference fringes here. And I can do my polarization phase shifting here. I can use my polarization mask, so I'm not sensitive to vibration. And if I now put in my little window there, the same setup as before, but I'd put in a window, even if this is a thin little guy with surfaces almost parallel, reflections, they will not bother me as long as this is thicker than the coherence length. In fact, I could be very clever here. I mean, I can test this in transmission here, but I could also vary this path length here, and I could look at the interference of the light reflected off the first surface with the light reflected off here, or the light reflected off a second surface with the light reflected there. Simply by changing delta L here, that will change which reflection is coherent with a beam reflected off of here. And so this is a true picture here of long coherence length and then using this system for the short coherence length. And these terrible fringes go away. So it's a complicated system. Costs a lot of money. Fortunately, you can sell it for a lot of money too. It enables you to, with a Fizeau, you can do the polarization phase shifting. But the bigger thing is I can really get rid of these spurious interference fringes and get a nice clean beam. Because sometimes people are making little windows that are very thin and surfaces are almost parallel, and they really have a lot of trouble testing them. And this gives us a way of testing them in transmission, or testing by looking at the reflection, or looking at the reflection. So I don't like complicated things, and I don't like expensive things, maybe I should say. This is not so complicated, but there are a lot of high quality optical components here. But it really works well in cases where you know, for testing windows that you just can't test otherwise because of these spurious interference fringes. So do you understand basically how this works? Okay. Any questions? Well, I think I'll stop at this point. What we're going to do next class, well, next class we're going to have an exam, but after that we'll talk about measurement of window wedge and a lot more things to talk about measurement of flat surfaces, and then we'll go on and talk about measurement of curved surfaces and so on. So I'll see you in a week and I guess it's going to be a week and a couple of days. So have fun. Who do we play in football this weekend? Might be the first question on the exam. Well, you're in luck, because we don't play anyone in football this weekend. We had a week off. Okay, so I'll